In today's lesson, we're going to be looking at the sum and difference rule for derivatives. So in the last lesson, we had taken a look at the power rule. Again, if you missed that, I'll link that at the top right-hand corner. But essentially, after our last lesson, we were in a situation where we could take the derivative of a base of x to any real number. But we didn't really know how to take the derivative of the sum or difference of these ideas. And that's what today's lesson is about. So given two functions, let's say the f and g, and let's suppose here that they're differentiable functions. So that means you can take the derivative of them and they exist. How do you go about taking the sum? Well, it turns out the sum is differentiable, and the derivative of the sum of those functions is just the derivative of each one individually. So here we're using Leibniz definition, using dy dx, to go ahead and calculate our derivatives. So these are the derivatives with respect to x. Equivalently, you can use the other form that we have here is f plus g, which is a function itself, prime. So the derivative of the sum of that function is just the derivative of each one individually and then sum together. This exact same rule works with subtraction as well. So therefore, if we change this to subtraction or subtraction or subtraction, again, that'll work just the same. I'm not going to go ahead and show the proof of this result here. It's fairly obvious. The result comes from the fact that derivatives are limits, and limits have the property that the limit of the sum is the sum of the limits, and the limit of the subtraction is just the limit applied to each function, then subtracting the result. So let's go ahead and see some examples of this. So in our first question here, we have a function f at x. The function here is 2x to the power of 4 to the root of x, and we would take the derivative. Well, now I know I can apply that derivative to each portion and just add the result, in which case the derivative of my first term will be 8x cubed, right? Drop down the 4 and then subtract 3. Keep in mind this root of x is really x to the power of a half. So in which case here we have here 2x to the 4th plus x to the power of a half. So now the next term I'm going to drop the half down, put the x back down, subtract 1, and you get x to the minus a half. And that'll be f prime at x. Okay, let's look at another. So for the next one here, same idea. We have a function g at x, and I want to take the derivative individually. So we're going to take the derivative. Now this time we're taking the derivative with respect to t here. So the derivative with respect to t of this function, we can apply that derivative individually. So this would be the derivative with respect to t of 1 plus the derivative with respect to t of 2 over t plus the derivative with respect to t of 3 over t squared. Now when I go ahead and do that here, the derivative of any constant is 0. Well, this 2t here is really, it can be written as 2t to the negative 1, in which case this will be negative 2t to the negative 2. And likewise, this can be written as 3t to the negative 2, in which case the derivative would be negative 6t to the negative 3. So therefore, g prime at t is negative 2t to the negative 2 minus 6t to the negative 3. And we have our derivative. Now just a quick comment on this idea of with respect to t. This function was a function in t. It was a function expressed as t, so the derivative with respect to t, in this case, it applied normally. Now if we would have taken this exact same question, and let's say I said, what's the derivative with respect to x of this expression here? Well, now the derivative with respect to x of this expression here would be viewed as 0. And the reason for that is because these values here would be considered to be constant terms as the derivative is concerned, and in which case by doing that, the derivative would be 0. All right, let's look at another. For our next example here, we want to take the derivative of the following function. So let's use Leibniz notation here. Again, if you need a refresher on Leibniz notation, I'll link it in the top right-hand corner. But essentially, we want to take the derivative of our function g with respect to t here. So therefore, using the sum and difference rule, we know that we can apply that derivative individually to each component here, each term. So this would be the derivative of a with respect to t, plus you have the derivative with respect to t acting on b over t, plus the derivative with respect to t acting on c over t squared. And now here, the assumption here is that a, b, and c are constant terms. So you treat them as a numerical value, real number. So now when we go ahead and take our derivative of our function g with respect to t, well, the derivative with respect to t of a is viewed as a constant, will be 0. The derivative with respect to t of this expression here, it will be best to write this in exponential form. So really you should realize b over t written as b times t to the negative 1. Therefore, when we take our derivative, we apply the power rule, drop down the negative 1, and this becomes negative bt to the minus 2. And again, we're going to rewrite c over t squared as c over t to the negative 2. And now we take our derivative with respect to t, and we get negative 2 ct to the negative 3 this time here. Rewriting this and simplifying, we get negative bt to the negative 2 minus 2ct to the power of negative 3. And again, just rewriting it as a fraction here, we have negative b over t squared minus 2c over t cubed. And this would be the derivative of g with respect to t. And notice here, before we move on to our next question, that if I were to take the derivative of g with respect to x, or any variable that isn't t, your derivative would be 0. The reason for that is when you take the derivative, let's say, with respect to x, this is not a function of x, this is a function of t, and therefore everything else would be viewed as a constant. So if I go to take the derivative with respect to x, this would all be viewed as constant values, in which case the derivative with respect to x in this situation would be 0. All right, let's look at another problem. So for this question here, it's the same idea. What we want to do here is we want to first write everything in exponential form. So this would be h at r is going to be, this would be r to the 2/3, plus this will be 2 times r. Again, this is the square root, so really there's a little 2 here. So this would be r to the 3/2. Now I can go ahead and take my derivative, in which case this is r prime at x is 2/3 r to the negative 1/3, plus drop down that 3/2, and then subtract 1, we left with a half, and we can go ahead and clean this up, and I get 2/3 r to the negative 1/3 plus 3r to the half. And that's h prime at r. All right, let's look at the next question. So for this question here, what they want us to do is find the equation of the tangent lines that pass through the point 2 minus 3 and are actually tangent to y equals x squared plus x. Okay, so for this question here, it's a little bit different. You have a function, so it's y equals x squared plus x. Just as a rough sketch, let's assume maybe it looks something like this. And then we have this point that's not on the graph. Notice here, the point 2 minus 3 is not on my actual parabola x squared plus x. So let's assume let's say it's somewhere over here, just as an example. It doesn't have to be to scale right now. That's not the point of the diagram. Just want to show you. So you've got this point 2 minus 3, and you have this tangent line that crosses through the point 2 minus 3. Now, it turns out in the question, they tell us here that we actually have 2 different tangent lines. But we don't really know that. If you look at this question in general, not looking to make this to scale here, but just you have 2 tangent lines on your parabola, and both those tangent lines, when you extend those tangent lines, they actually cross through the point 2 minus 3. Our goal is to find what these tangent lines are. Well, I know this point here is going to be x, f at x. But I know what f at x is. It's going to be x squared plus x. So therefore, what do I know? Well, I know that the slope of this line here can be expressed as the change in my y. The change in your y will be y2 minus y1, and then over x2 minus x1. So the slope can be represented as x squared plus x plus 3 over x minus 2. But it is also equal to, the slope is also equal to f prime at x. Now again, we don't know what the x value is, but I know here if I take a look at my function y, I know that y prime is going to be 2x plus 1. So therefore this is going to be 2x plus 1. So therefore we have 2 different ways of representing the slope. In one hand, the slope is x squared plus x plus 3 over x minus 2. On the other hand, the slope is 2x plus 1. So equating these two here, we have x squared plus x plus 3 over x minus 2 has to equal 2x plus 1. Well, fairly easily I can go ahead and multiply across by x minus 2, in which case I get x squared plus x plus 3 equals, we get 2x squared minus 4x plus x minus 2. Making a little room for ourselves here, we have x squared plus x plus 3 is you get your 2x squared minus 3x minus 2. Bring everything to one side, we get 0 equals x squared minus 4x minus 5, and this will actually factor quite nicely into x minus 5x plus 1. So we actually get 2 values here. One is 5 and the other is negative 1. So it turns out that the 2 points on the curve y equals x squared plus x, whose tangent equations cross through the point 2 minus 3, Those 2 points are going to be point number 1, 5, f at 5, which would be the point 5, and then that'll be 30. And the second point, point number 2, will be negative 1, f at negative 1. Again, notice here I'm not subbing this into my derivative, I'm subbing into my original function, in which case here we get negative 1 and 0. So putting this together and finding our tangent equations here, we have our point 530 and the point given to us 2, negative 3. We're going to find our tangent equation from these 2 points, and likewise for our second tangent equation. So finding our first tangent equation, we have to find our slope. Slope will be, doing rise over run here, you see that we get 33 over 3, which becomes 11. So the slope of the first tangent equation is 11. Subbing this into my y equals mx plus b form, I can choose either point to sub in. I chose to sub in the point 2, negative 3 here. Subbing that in and solving for b, we get a b value of negative 25. So the tangent equation, one of them, is y equals 11x minus 25. Let's find the second. Going through the same process here, doing our rise over run, we end up getting 3 over negative 3, which gives us a slope of negative 1. Subbing that into my y equals mx plus b, and again, you can choose either point. I just chose the same point again, 2 minus 3. Sub that in, you can find your y-intercept of negative 1, and therefore the second tangent equation is y equals negative x minus 1. All right, let's look at another problem. Okay, for this question here, they want us to show that the following degree 3 polynomial here has no tangent with a slope of 4. Well, if this has no tangent with a slope of 4, let's first take our derivative to get a general expression for any tangent, in which case we get 18x squared plus 5. If this has a slope of 4, that means I can set this equal to 4 and I'll be able to find an x value that'll satisfy that. Going ahead and doing this here, we can already see if I go to subtract the 5, I end up getting negative 1 equals 18 squared, in which case I get x squared equals negative 1 over 18. Well, we have a problem here. The problem is the left-hand side is always positive. The right-hand side is always negative. There's no real numbers that you can go ahead and square, and that'll give you a x squared value of negative 1 over 18. And therefore, there is no degree 3 polynomial whose derivative will yield a tangent line having a slope of 4. Okay, that concludes the lesson regarding sum and difference rule. Just a minor extension of the power rule. Please feel free to review these questions here, especially the tangent equations. A lot going on here, so try to make sense of it. See my other playlists if you need any help with other calculus lessons. Thank you.